Okay, Unit 4 questions, continuing. We're going to carry on from question 4. The first bit of question 4 is calculate the value of this thing. You can just press buttons in your calculator, or you could do it without a calculator. Tan repeats every 180 degrees. So if we add 180 to this, or take 180, it'll give you the same value. If I add 180 to this, it'll give me 60. Tan of 60 is root 3. Minus 2 times root 3 is minus 2 root 3. Right, part B, which is the major points, is we need to sketch these two graphs. Okay, I'm going to use a pencil for this in case I go wrong. Let's start with the 2 sine x minus 60. Well, let's do sine first. If I do a little sketch of sine as best I can. Okay, there's sine. The first thing I'm doing to it is I'm moving it 60 degrees to the right. So that's going to go there, that's going to go there. This is going to go 60, 120 is going to be around about there. So that's going to go about here. So it's going to be something like that. So that is just the x minus 60 bit. Move 60 degrees to the right. Now I need to multiply it by 2. So this point here is going to go to there. This point is going to go to there. That point remains the same. That point remains the same. And this point is going to go twice as high up to about there. So this is 2 sine x minus 60. Let's go over that in a different colour just so we can see it properly. We know that's the one we're dealing with. Oops. All right. Minus 2 tan x. Let's do tan very quickly. Tan of 45 is 1, so it goes through there. And it never gets to 90, so it's going to go through there. And never gets to minus 90, so there's tan. And minus 2 tan is going to be reflected in the x-axis and stretched out a little bit. So that's going to go to there. It's going to be something like that. There's not much of a turn in that, but if we squish the y-axis down, you'll see that tan does do, even minus 2 tan does have a curve there, a nice curve. But because of the scale, you can barely see the curve. So this graph here is minus 2 tan x. Now we need to look carefully at our domain here, because I've drawn tan between 90 and minus 90, but the question wants us to draw them between minus 180 and 180. So this line is going to, tan just carries on every 180, so that's going to go down to there. And this one is going to come up from here to about there. So that is minus 2 tan x. So that's our sketch. We need to show the coordinates of the points of intersection. This one here is 60. That's 60 degrees. So this one here is minus 180 plus 60. So that's minus 120. And we also need to do this one. We need to work out if x is 0. What if x is 0? You've got a sine of minus 60. Sine of minus 60 is minus sine of 60, and the sine of 60 is root 3 over 2. So sine of x minus 60, of sine of minus 60 is minus root 3 over 2, times by 2 is minus root 3. So this is minus root 3. I hope you got all that. You can obviously put that in your calculator. The rest of the values, the 180s, the 180s and the naught are fairly clear from the diagram. Bit of a mess. Hopefully yours is clearer. I could rub out the pencil lines to make it a bit clearer if you wish. Explain how you can use the graph. This is part C now. Explain how you can use the graph to identify solutions to the equation y equals 2 sine x minus 60 plus 2 tan x. Well, that equation, y equals 2 sine x minus 60 plus 2 tan x equals naught. Well, this is a strangely written equation. This thing is equal to naught when that is equal to minus this. In other words, when this is equal to that. So all we're looking for are the places where our graph crosses. So those two places would be the solution. So x here is somewhere around about 35, and this one here would be something like 120-ish. So those are the two places where our two graphs cross. So that's the explanation. And the number of solutions are that there are 2. So for part C is explain how you use the graph, where the graphs cross. How many solutions are there? There are 2. Alright, question 5. We need to find these values. We need to solve the values for theta that are between 0 and 180. Okay, we have 2 different trig functions here, which is always tricky. Fortunately for us, the angle is the same. So what I could do is I could divide both sides by cos 3 theta plus 20. So I'll have 4 root 3 sine 3 theta plus 20 over cos 3 theta plus 20. And that equals 4. Well, sine over cos is tan, assuming that the angle is the same. So this bit here is just tan of 3 theta plus 20. And I'm going to divide by 4 root 3. So that's 4 over 4 root 3, which is 1 over root 3. If tan of something is 1 over root 3, some of you may remember, but we can actually just write down what the angle is. 3 theta plus 20 has to be 30 degrees. That's the primary value. We now need to draw a quick cast diagram to find out what the other values are between 0 and 180. C, A, S, T. Well, 30 degrees is there. The only other value which would give me the same value of theta, give me the same value of tan, would be down here somewhere. So if that's 30 degrees, this is 30 degrees. So it could be, that would be 210. Now we're not sure how many times we need to go around here because it's written like this. So what I can do is, if I know that theta has to be between 0 and 180, then if I squeeze in here 3 theta plus 20, then I know that this has to be 20, and 3 times 180 is 540 plus 20 is 560. So I know that 3 theta plus 20 can be anywhere between these two values. So I can keep going. Right, so we've got 30, we've got that one, we've got that one. We can go around again, that's 360, so that's 390. and we can go around even further. 360, 450, 540, 570. That's too big, so we can't use that one. So 3 theta plus 20 is either 30 or 210 or 390. So let's work out what 3 theta is for these. So what theta is rather for these. So if it's 30, then it's 3 theta is going to be 10. So theta is going to be 10 over 3. And next one is this. Oops, that's not theta, that's a 20. So that's going to be, take the 20, that's 190. 190 divided by 3. And the last one is 390, take 20 is 370 divided by 3. 370 divided by 3, and you can obviously work those out more accurately on your calculator or in your head. Alright, number 6. A teacher asks one of her students to solve this equation. And the attempt is shown below. If you work through the attempt, it all looks pretty good until you get to the very last bit. Just like in question 5, what the student's done, the student has worked just this bit out. If 3 theta plus 20 is 30, worked out what theta is, and then applied the transformation to that, or define it, used that value in the cast diagram. You can't. You need to use these values in the cast diagram. So that's the only mistake that the student has made. So once the student had 2x equals 150, we also need to work out what other values could they have. And because we're dealing with cos, 150 would be there somewhere. So cos is negative, so it's going to be here. That's 150. This is 30. This is also 30, so we can have 210. Our domain is x up to 180, so 2x goes up to 360. Well, you can see on here there aren't any more values go up to 360. So x is 75, which is the value the student had, or half of 210, which is 105, which is the one that they were missing. Last one. Question 7. It says a buoy is a device which floats on the surface of the sea and moves up and down as waves pass. For a certain buoy, its height above its position in still water is modelled by this equation. Sine curve, as you can see, goes up and down. You knew that anyway. A buoy going up and down, sitting on the sea, would go up and down as the waves move it up and down. So this is our model. The first bit, 3 points, is to sketch the graph. Well, because I've got 180 t in here, if this was just t or just theta, then this is what it would look like, and that would be 180, 360, 540, and so on. Because I've got 180 t, this value here is when t is 1. That's when t is 2. That's when t is 3, and so on. So these are what the labels along my x-axis or t-axis would look like. Now I've drawn sine here, but we want half sine. So what we would actually have is a curve that goes through 1, 2, 3 rather than 180, 360 and so on, but it's half the height. So the curve I'm actually looking for goes like this, and we're going up to t is 10. So that lower curve is the curve that we're looking for. And it asks for us to show where it cuts the t-axis, the points of intersection. There are my labels, 1, 2, 3, 4, and so on. Part B says, write down the number of times the buoy is 0.4 metres above its still water position during the first 10 seconds. Well, above it, so 0.4 metres above, well 0.4 is about there. I'm just going to draw a line at 0.4. The number of times it's above this line, so once, twice, 3 times, 4 times, 5 times. There are 5 occasions when the waves take it above 0.4 meters. So for part B, there are 5 times. And there they are. There's once, twice, 3, 4, 5 times. Part C, you always get this kind of question in a modelling question that asks you to give reasons why this might not be realistic. Well, I don't know about you, but whenever I've seen the waves come in at the beach, they never come in quite as uniformly as this. So that would be my criticism. It's unlikely that waves will behave so tidily, so uniformly across a period of time. There's going to be big waves and small waves and longer times between waves and shorter times. So anything down here about it not being a realistic model of how waves work would get you the point. And that's Unit 4 test. Hope it helps.